So we're going to get as far as we can in Chapter 6 review today. And then if we have to, we'll go to next Tuesday to finish the review. And my hope is that if that's the case, we can finish in time so we can do some lab prep in here, pre-lab stuff. And if you have any questions too about the procedure itself, if I've said, I know I've said this before, when you're preparing for a lab, and aside from setting up your lab notebook so that it'll be useful and so that you can perform the lab from your lab notebook, there's nearly always, in fact, I think I can say always in this class, you'll always have a principal objective. So keep that in mind. What are you trying to accomplish? You may want to put that in the introductory statement too. May help you focus. And so when you've got your data and you're trying to make sense of it, that principal focus should inform your.
Yeah, something weird's going on there somewhere, and it's not even showing up here.
Okay.
On the TV at the moment for some reason.
It's not going to interfere with my class, I don't think.
We'll get it fixed as soon as you don't have to get up in there and see what's going on with the extenders.
Okay.
Or not, we have to throw these down.
That'll make an interesting side conversation for the video. Okay, we'll talk more about that when we discuss the lab itself. So let's look at these that I've highlighted. See if we can make sense out of it. Let's see. Number 2. What's the kinetic energy of a 1.56 kilogram object moving at 94 kilometers per hour? Okay, here's what we're given. Well, the question is, what's the kinetic energy? I suspect that we're going to have to use, since we're talking about a single object, we're probably going to use that formula. We're given a mass of 1.56 kilograms. That is in SI units. So we can leave that one alone. 94 kilometers per hour. All right. That's in non-standard units. Right. SI units would be meters per second. So this has to be meters per second, kilograms here, in order for this to give you units of joules. So this, we need a unit conversion here. Remember when you have 2 units or more units in the converted unit, do one at a time. All right, so we want to get down to meters. We have 1,000 meters in a kilometer. That's done. Now we want to change hours. Right. Denominator, numerator. How many seconds in an hour? Right now. 60 minutes in an hour, 60 seconds in a minute, 60 times 60 is 3,600. Okay. So we got rid of those. Now we can, that'll give us a usable velocity value. 94 and 1,000 divided by 3,600 is 2.61. Oops. What by scientific notation? 26.1. Let's just give it another one to avoid rounding errors. Okay, so now that we know these values, we can put them in our formula. 1.56 kilograms, and this is 26.11 meters per second squared. Okay. I already got that one in there, so I'm gonna square it. And then times 1.56, and then take a half of that. And now I'm gonna round it off to 3 places. 532 joules. Oh, kilojoules. Okay. Which way do we need to move this? If the unit gets bigger, the number has to get smaller. So that means we got to move to the left. 3 places. 1, 2, 3 places would be 0.532 kilojoules, but it's in scientific notation. So we got to move it over here. 32 times 10 to the minus 1 kilojoules. That should be up there somewhere. A. Just when you think you have the answer. All right. Let's see, number 3. It's already starting to get loose on it. Let's try a fresh one. Which of the following statements? Excuse me. Oh, did I get? 5, 6. 6. All right. Which of the following statements correctly describes the sign of Q and W for the following exothermic process? So if we're going from gas to liquid, we know that's going to be exothermic. Because as this condenses into a liquid, it has to give up that heat. We know this is exothermic. Exothermic. And the problem tells us it is. We're also given pressure of 1 atmosphere and temperature of 370 K. That's everything we're given. Okay. All right. So if we're looking at Q and W, let's see, Q versus W, and we only care about the sign. Right? If it's exothermic, we know that Q is going to be negative. Right? That's an easy one. Let's see. How about W? Well, is there any work being done? If the pressure is constant and the temperature is constant, then I think a picture would help. If we have our piston here, and we've got water vapor, the gas, and it's going to liquid. We maintain the pressure, then that piston's going to drop, isn't it? And a decrease in volume means work is being done on the system. So if work's being done on the system, this has to be positive. So it's negative and positive. C. Okay. Righty. Right. So who's next? That number 7. Let's see if I can move it up a little bit. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atmosphere. How much work is performed on the surroundings? Ignore significant figures for this problem. Okay. So the calculation of work in this case would be minus P delta V. Pressure is going to be constant, correct? Yeah, at 1 atmosphere pressure. So this is constant at 1 atmosphere. in order to do the calculation for the volume, we need, what's the initial volume? And what's the final volume? The initial volume is 1 liter, expanded from 1 liter to 8.93. All right, 1 liter, 8.93 liters. So now we know that our calculation is -1 atmosphere. And then change of volume is final minus initial. So it's 8.93 minus 1 liters. Okay. So that would be 7.93, a positive value here, negative value there. So minus 7.93 liter atmospheres. Okay. But our answers are all in joules. So we got to do a unit conversion. So what's our conversion factor? Liter atmospheres per joules, and it's given to you in the problem. 1 liter atmosphere is 101.3 joules. I don't have to use my calculator for this one. 101.3, 7.93, go ahead and give it a negative sign. And this is minus 803, 8.03 times 10 to the second joules. And standard units would be, move it 2 places, minus 803 joules. That would be B. Right. Let's try number 12. Calculate the work associated with the compression of a gas from 121 liters to 80 liters at a constant pressure of 13.1. Oh, this is even simpler than the last one. Okay, if a gas is compressed, it's starting at 121.0 liters. So initial volume is 121.0 liters, and it goes to 80 liters. Final volume, 80. And it's at 13.1, a constant pressure of 13.1 atmospheres. So all we have to do is say pressure, and then final minus initial. Now, this is going to be a negative, that's a negative, so we're going to come out with a positive number, which means work is being done on the gas, and that makes sense. It's going from 121 to 80. Outside, the surroundings are doing work on the gas. 80, 121, 13.1 is 5.37 times 10 squared liter atmospheres. And let's see, we're in standard notation. So it'd be 537 liter atmospheres. That would be B. That's a unit of energy, liter atmospheres. It's just, sometimes it is, sometimes it isn't. Depends on what you're calculating. Now, joules is always energy. Liter atmospheres is energy when we do this type of calculation. All right. Okay, we got several. 14 through 17 based upon this first paragraph. Okay, so what does it say? A gas in a 1 liter bulb at standard temperature and pressure is connected via valve to another bulb that is initially evacuated. Okay, so we've got this 1 liter bulb. All right, at standard temperature, in this case would be 25 degrees C. And pressure, 1 atmosphere. And is connected to another bulb. And let's see, doesn't say what size it is. It just says 0 atmospheres. This is a vacuum. Okay, so what happens when when the valve is open? Right, we know what's going to happen. We're going to get some of this gas is going to rush over there until we get equilibrium. We've done a calculation with gases like this before, but now we're looking at it in terms of energy and work, heat and work. So what's true about the value of Q? Well, it says, doesn't it say at standard temperature and pressure? So this whole system, everything here is at 25 degrees. And it stays at 25 degrees. Remember, heat is only measured when there's a difference in temperature. Heat can only move with a difference in temperature. So Q in this case is 0. There's been no heat movement at all. All right, 15. What's true about the value of W? Well, the gas expanded, but did it expand against a pressure? No. There was no opposing pressure for this gas as it expanded, so it didn't do any work either. All right, how about delta E? Well, remember delta E is equal to Q plus W. If both of them are 0, then delta E is equal to 0. Okay, what's true about the value of delta H? Well, enthalpy is a thermodynamic potential for heat. This is actual heat measured. This is the potential. And if the pressure stays the same, then these two are equal. And the pressure did change. So that one's also 0. Oops. Is that the last one? Yeah. 17 was the last one. Now we're going to 18. Now, let me see. When are we going to explain why it moved? I think that comes in seconds. Be sure. Yeah. Yeah, we find out. I mean, if the gas is going to move and none of these are all 0, why did it move? That comes later. Okay, 18. Of energy, work, enthalpy, and heat, how many are state functions? Oh, I accidentally left the state functions bolded. Energy is a state function and enthalpy is a state function. So the other two, work and heat, are path functions. It does depend on how you get from point A to point B. But with energy and enthalpy, it doesn't matter. Just the current conditions is all you need. All right, 19. Which of the following properties are intensive properties? Okay. Let's say, rather than write them all up there, save a little time. Is mass an intensive property? No. The more you have, the more mass you have. That's an extensive property. Temperature. Yeah, temperature is an measured of average kinetic energy of the molecules in a substance. And it doesn't matter how much substance you have. Temperature is an intensive property. Volume. Now, the more you have, the more volume you have. So that's extensive. Concentration. Yeah, that's intensive. Right? Because you can have a 1 molar solution that's this big, and you can have a 1 molar solution that's that big. So far, Roman numeral 2 and Roman numeral 4 are intensive, and energy. Energy gets bigger with the amount. So the only two that are intensive properties are Roman numeral 2 and 4, which is C. All right, 23. All right, we got this equation considering the following propositions. The reaction is endothermic, exothermic. Enthalpy term would be different if the water formed was gaseous. Which of these propositions are true? Okay. C2H5OH is ethanol, the drinking kind. And we're combusting it. We're burning it in oxygen and making carbon dioxide and water. And if we do 1 mole, combusted 1 mole of ethanol, we would get 137 times 10 to the third kilojoules. A lot of energy. Okay, is this reaction endothermic? It can't be both. It's got to be either endothermic or exothermic. Well, the value for delta H is negative, so it's exothermic. Right? So that means 1 is true. That one's true. How about the enthalpy term would be different if the water formed was gaseous? They've listed the water under standard conditions as liquid. Yes, the enthalpy would be different because some of the heat that's generated in the reaction would go to converting water liquid into water vapor. Right? So the value would probably be lower. It'd be a smaller value. Maybe not by much, but it would definitely be different. So 3 was also true. Right? So which of the 4 propositions are true? 1 and 3? Wait a minute. Oh, 2 and 3, excuse me. Not endothermic, it's exothermic. 2 and 3. All right, 24. How much heat is required to raise the temperature of 5.75 gram sample of iron with that specific heat from 25 to 78? Okay. Here, all we need is the simple equation of Q equals specific heat times the mass times the change in temperature. Okay. This is one of those cases where the temperature, we don't have to change the temperature to Kelvin. Actually, it would work because we'd subtract the final from the initial and get a value that's exactly the same size as Celsius. So it really wouldn't matter. Sometimes the specific heat is listed as joules per gram K. But the value is exactly the same as if you use degree C. Right. Okay, so let me leave that there. And what was our value for 0.450? 0.450. That's your S. Mass is 5.75 grams. Okay, so we check our units, right? It's going to cancel the grams. That's good. And then final minus initial from 25 to 79.8. 79.8 comes first because it's final in 25. Okay. So I'll go ahead and do this one. Sometimes it's useful to do these just to be sure that my P is correct. 0.45 5.75. And 79.8 minus 25. So I get 1.42 times 10 to the second joules. Or in standard notation, 142. Yeah. E. Okay. All right. 24, 26. .5 gram piece of aluminum with a molar heat capacity. All right, so this is not specific heat. This is molar heat capacity. Instead of grams, it's in terms of moles. It's heated to 82.4 degrees and dropped into a calorimeter containing water with that specific heat, initially at 22.3. Final temperature is 24.2 degrees. Calculate the mass of water in the calorimeter. Okay. So in this case, let's put what we know up here. The mass of aluminum. Put it over here. Mass of aluminum equals 32.5 grams. Okay. And molar heat capacity for aluminum is 2403. Molar heat capacity for aluminum. Let's see, should we use S? I guess so. The units will tell us what it is. 24.03 joules per mole degree C. Okay. Let's see, 82.4 degrees is the initial temperature of the aluminum. So Ti for aluminum is 82.4 degrees. Okay. Let's see. The specific heat for water equals 4.18 grams per, joules per gram degree C. What else do we know? We don't know the mass of the water. That's the unknown. We know the initial temperature of the water is 22.3 degrees. Water, 22.3 degrees C. And the final temperature of everything is 24.2 degrees. Yeah, 24.2 degrees C. We given anything else? That's it. Okay. We're going to need to know the number of moles of aluminum in order to use this value here. So we might as well go ahead and convert it. Right. Aluminum, 26.98 grams per mole. So 26.98 into 32.5. 1.205 moles of aluminum. Okay. Now we're going to set up our equation. Remember, calorimeters are isolated systems. That is, everything that happens in that calorimeter stays there. All the calculations have to end up as 0. So we would say 0 equals the heat change for aluminum, the heat change for water, and we assume that the calorimeter has no effect. I mean, we know it does, but we're not given that information, so we're stuck right there. So we have these two to calculate. So what's the Q for aluminum? Well, it's SM delta T, just like before. So this is our S value, 24.03 joules per mole degree C. And well, instead of mass, we have moles, so it'd be SN delta T. 1.205 moles. We know we're heading the right direction because these two will cancel. Now we want to cancel the degrees. So what's the initial temperature? What's the final temperature? 24.2. Right? Because when they come to equilibrium, the metal is at the same temperature as the water. And minus the initial temperature, which is 82.4. Right? If we get those reversed, then we're going to get the wrong answer. All right, then we're going to add the term for water, which would be, what's the S for water? 4.18 joules per gram degree C. Then the mass of the water is unknown. And then the change in temperature is final, 24.2, just like the first one. The initial temperature of water is 22.3. There we go. So that's the thinking part. All you have to do now is crunch numbers. I guess we ought to do one because I haven't done one yet. So this difference here is what? 24.2 minus 82.4 is minus 58.2 minus 58.2 degrees C. Okay, so times 1.205 and times 24.03. So the first term here, 0 equals, this first term is minus, I'm going to put this in standard notation. 1, 2, 3. 1,685.2 joules. Okay. Then we'll have this term. So 24.2 minus 20 minus 22.3 is 1.9. All right, so 1.9 times 4.18 is 7.942 times the mass of the water. Okay. Now we got to get all our knowns on one side and our unknowns on the other side. So this one comes over here as a positive. 1,685.2 joules equals 7.942 mass of the water. And then the mass of the water is this number divided by that number. Right? Let's see here. I get 2 grams. Okay. Agrees with the key. This is the most tedious part here. After you finally set it up, very methodically set it up for these terms, then solving the equation is where you could trip over a matchbox. Seen old Monty Python skits. Look for the one for Twit of the Year contest. It's funny. At least it is to me. I referenced tripping over a matchbox. That was one of their obstacles. The Twits had to go around the ball field and jump over a matchbox, and they kept tripping over it. All right. Okay, next one. How we doing? Okay. 27. 45.9 gram sample of metal is heated to 95.2 and then placed in a calorimeter containing 120 grams water. Final temperature of the water is 20. What metal is used? So in this case, we're comparing the determined specific heat for the metal. In this case, the variable symbol is C, but it means the same thing as S, specific heat. We used to use C, small c in the old days because we did our calculations in terms of calories of heat rather than joules. Now that we do joules, I think that's why they switched to S. But it means the same thing. Okay, so let's see if we can extract these from the board rather than writing them on. Normally, I'd write them down on the board what we're given so that we don't make any mistakes, but I'm going to try to do it without that. So we have we have metal, and we have water. Okay. So for the metal, we have an unknown specific heat for the metal. Then we have the mass of the metal, which is 45.9 grams, excuse me. So that's the correct units. And then it's heated to 95.2. So that's the initial temperature. 95.2 degrees C. And the final temperature is the same for both water and the metal, 24.5, right? 24.5. All right. Now we have water. Go ahead and put the specific heat for water as 4.18. 8 grams. Why do I keep doing that? Joules per gram degree C. And then the mass of the water is 120 grams. The initial temperature is, final temperature, no, it's 24.5 minus the initial temperature, 21.6. There we go. Now we just solve for this value right here. Do I need to do that one? Nobody cares. All right. That's 24.5 and 21.6. So this is 2.9. In case I have to come back and check it. 120 times that and 4.18. That's that. This value is 145, 4.6 joules. Okay. On this side, we have 24.5 minus 95.2, which is minus 70.7 times 45.9. And that's minus 3245.1 times the specific heat. That's equal to 0. So now we get this one on this side. It becomes a negative 1454.6 and negative 3245.1. Yes. So this specific heat is going to be this one divided by that one, and the negatives cancel. So let's see if I got them in the right place in my calculator already. Yes. So I get 0.448 joules per gram degree C. That means it's iron. Okay. And scroll a tad, go to number 28. Okay, you take 295.5 grams of a solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. All right. We didn't talk about the heat of fusion. The heat of fusion is like the calorimeter constant. It has the mass term, the heat of fusion. Let's see. That would be, I guess it'd be S with a small f on it. This would be in terms of how much heat does it take to melt this many grams at its melting point. Okay. Water temperature. Okay. So we're saying that the melting point of this solid is 30 degrees. Yeah. Because water temperature is at 85.1, but its final temperature is at 30 degrees. That's the only thing that makes sense. If this is the case, then you only need one other term. So the amount of heat, let's see, we can do it this way. 0 equals Q for the fusion plus Q of the water. And that should be equal to 0. So Q of the fusion would be this value, and that's what we have to determine. SF times the mass, which will cancel the grams and give us joules. Because everything in here, each term is ultimately joules, heat term. So are we given the mass? Yeah, 295.5 grams. 295.5 grams. Okay, then we do the water. The water is going to be our customary 4.18. 4.18 joules per gram degree C. And then the mass of the water is 425. And then the water changes from its final temperature is 30. Its initial temperature is 85.1. Okay. Yeah, I think we're ready. So let's do this calculation right here. Now, the way I was taught initially was find out how much heat is given up by the water, and then equate that to the amount of heat that's here, and then solve that half. But I like this way better. It's the same thing, actually. We'll bring this over here. They're equal to each other. We just change the sign. Let's see, 30 and 85.1 minus times 425 times 4.18. So this term right here is minus 97885. Yeah, joules. And this one, of course, is 295.5 times SF minus that one. So bring that one on this side, it becomes positive. And this is 295.5. Specific heat, then we just need to divide this one by that one. 295.5. And I get SF, specific heat for this one is 331 joules per gram. Okay. It's all based upon this thing right here. what you have to do is decide, once you get it set up, is how many terms are going to be in it. Terms in this one will always be 3. Specific heat, mass, and change in temperature. Unless the molar, unless it's molar heat capacity for water, and then you use, you have to change that into moles. But it's going to have 3 terms. This one only needed 2 terms, like our calorimeter constant, our calorimeter calculation only needs 2 terms. It needs the calorimeter constant C times its joules per. In that case, it'd be change in temperature. So that's the difference here. For calorimeter constant is joules per degree C. For fusion, heat of fusion is joules per gram. So that's where dimensional analysis really comes in handy. Watch your dimensions. They will tell you whether you're on the right track or not. All right. Okay. Who's next? 32. In the lab, you mix 2 solutions, each originally the same temperature, and the temperature of the resulting solution decreases, which the following is true. If you add the 2 solutions and the temperature decreases, that's an endothermic process. So A is not right. It's not releasing energy. Like A is false. The energy released is equal to SM delta T. Well, we don't know. It's not exactly equal to SM delta T because there are 2 solutions. You added 2 solutions together. They might be at the same temperature, but the final temperature is going to be different, and the mass of each might be different. The specific heat might be different. So we can't just say that the energy released is SM delta T. That's too simple. That doesn't cover all our bases. So I'm going to have to say B is also false, simply because it's not complex enough. Chemical reaction is absorbing energy. Yes, it's endothermic. And since we have E more than one, we have to look at D also. The chemical reaction is exothermic. Well, you can't be both. It's either one or the other. And so E is also false. Okay, so C is the best answer out of that group. (36) Exactly 123.7 joules will raise the temperature of 10 grams of metal from 25 to 60. What's the specific heat capacity? Now this is simple. This is one where you do only need that equation, because it asks you for this value right here, and it gives you the amount of heat, 123.7 joules, equals our unknown times what's our mass, 10 grams. And the change in temperature. So from 25 to 60, 60 is final. Minus 20, right? No, 25. Go. 3C. So now all we have to do is say, all right, I might be able to do this one in my head. 35, right? Times 10 would be 350. So S is equal to 123.7 divided by 350. Is that about a third? The one that's closest to a third in there is B. 0.353 joules per gram. Pretty simple. Okay. That way you don't have to waste time with the calculator. Move on to the next question. Those other values are not reasonable for metals. Most metals have, as the only ones I can think of, have a heat capacity that's less than water, 4.18 for water. So they need to be less than that. Maybe A could be possible. But C and D, I don't think so. We found our answer anyhow. 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size because. All right, let's take these one at a time. Okay. Everybody see the movie that, let's see, Dumb and Dumber? The first one, right? Where the dumber got his tongue stuck to the pole. Okay. Okay, that's what we're talking about here. If he'd have chosen a wooden fence, it wouldn't have happened. Okay. Why does the metal feel colder than the wooden fence? Right? This is steel. And this is wood. So why is this one colder? It feels colder. When something feels colder, the temperature drop is more pronounced. Okay. The specific heat capacity of steel is higher than the specific heat capacity of wood. Well, let's look at it this way. The amount of heat that's transferred is the specific heat of the pole and times its mass times the change in temperature. Okay. The specific heat for this one is for wood times mass times change in temperature. So we're pretty sure that these two are different. The specific heat capacity is different. And we can say that the masses are the same. But just as an argument. Temperature change might be a little different. So what happens if the amount of heat transferred, if we hold that constant, then that means that we've got an inverse proportion. So the difference in temperature, as the difference in temperature goes up, the specific heat goes down. So if the change in temperature is, if we feel it colder, then the change of temperature is greater for this one. Right? If you feel it's colder, change in temperature is greater. That means that this one has to go down. As compared to this one, which say if we hold it constant, this would be lesser. And this would go up. So the specific heat capacity of wood should be higher than that of the post. Now, I said steel post. It could be aluminum for all I know. No, it couldn't, because it said steel fence post. Okay, so which one of these fits? The specific heat capacity of steel is lower than the specific heat capacity of, yeah, that fits. Okay. It's probably hard to follow that reasoning, isn't it? Oh, two of the above. Uh-oh. All right, so A was out. B is a good answer. Does C have any validity? Steel has the ability to resist temperature change better than wood. That's the definition of heat capacity. The temperature change of steel is going to be much greater because its specific heat capacity is lower. So steel does not resist temperature change better than wood. Wood is the other way around. It has a smaller change in heat capacity. So that one's false. And then we have to look at D. The mass of steel is less than wood, so it loses heat faster. Well, our argument held the masses the same. Now, obviously, the mass of wood would have to be, the volume of wood would have to be a lot bigger to match the mass of the steel. But if we don't hold mass constant, then our argument falls apart. We can't go anywhere with it. Because instead of having two variables, one against each other, now we got three variables and we don't know which one's which. So we're kind of stuck. And we have to stick with the difference in heat capacity. Now, I'm not sure if that's the same argument I gave you in the written problem. It's been a while since I wrote that up. All right. Oh, we got another. Oh, okay. So we got this equation. 3, where we're burning ethanol again. And if we burn 1 mole of ethanol, then we get 1,370 kilojoules. So when 21 grams, I guess I better put that up there. C2H5OH, 3O2 yields 2 carbon dioxide, 3 water. 2 water, and that's probably liquid, gas. So we're starting off with 21.1 grams. Okay, is oxygen excess? Doesn't say. It just says when that much is burned. So oxygen must be excess. That's the only way we can get to the answer. Okay, so we have to find out how many moles this is because the value of delta H is in delta H equals minus 1.37 times 10 to the third kilojoules. And our answer is in kilojoules. But this is per 1 mole of ethanol, per 3 moles of oxygen, per 2 moles of CO2, and per 3 moles of water. So in order to make it useful for us, this is per 1 mole of ethanol. That's my abbreviation for ethanol. So we need to convert this to moles. All right. So 2 times 12.01 for that carbon. We have 6 hydrogens. 1.01, and then 1 oxygen. So we had to find out the molar mass of ethanol. 12.01 times 6.06, 16. 4608 grams per mole. Oh, it gives us the value? Okay, I guess we better use that one. Otherwise, it'll be a little off from the available answers. That's okay. All right. Let's see. Go, and then 21.1, and I get 0.458 mole. Okay, now we can multiply that times the delta H minus 137 third joules per mole. Okay, 37. So 6.27 times 10 to the minus 4 kilojoules. Our values are in terms of. Oh. No, that's not right either. All right. I put it in my calculator wrong. Let me try it again. 1.37. 3.458. That's better. 627. And the sign simply means it's exothermic. Times 10 squared. So it doesn't show the signs up there at all. So if we look at the problem, it says how much energy is released. Released means exothermic. So this is the amount of energy that's released right here. That's what the answer is, C. If it asks you what the Q is for the reaction, then it'll probably have a sign with it. But since the wording is energy released, then we're missing the sign. All right. Good. We're creeping up on total volume, let's see, 45. Total volume of hydrogen gas needed to fill the Hindenburg was 2.11 times 10 to the 8th liters. Quite a bit at 1 atmosphere and 24.7 degrees C. How much energy was involved when it burned? Okay. So we're given 2.11 times 10 to the 8th liters. That's volume. Liters, there we go. And pressure is 1 atmosphere. And temperature is 24.7 degrees. C. And we know that the delta H is minus 286 kilojoules for that reaction. So that's delta H is minus 286 kilojoules per, look at the equation, per mole of hydrogen. Okay. All right. In order to find out how much heat, we got to find out how many moles of hydrogen that is. All right. Got any ideas how to do that? Yeah. Mm-hmm. Exactly right. We need to know this one. PV equals nRT. The number of moles is equal to PV over RT. Pressure, 1 atmosphere. Volume, 2.11 times 10 to the 8th liters. Okay, our units are correct. This is atmospheres, that's liters. This is a 0.08206 liter atmospheres per mole. Okay, and then temperature is 24.7 plus 273. There we go. So that'll give us the number of moles. Seven. No, I didn't do that. Let's start this 24.7 plus 273. That's 298. 98. Okay. Now 0.08206 times that. And 2.11 exponent 8 and put those divide. That looks better. This is 8.64 times 10⁶ moles of hydrogen. Now we can multiply that times this value. 8.64 times 10⁶ moles. And the moles cancel, leave us with kilojoules. So 286. So it's in kilojoules. I get 2.47 times 10⁹. So it's not D. Yeah. Okay. A lot of energy. All right. Still got, let's see, we got till 10 minutes till, right? All right. Or is it 45? Oh, it's 45. Sorry. I got 5 minutes. Let's look at 46 then. Let's see, methane plus chlorine yields carbon tetrachloride plus hydrogen chloride gas, and it's exothermic with 434 kilojoules. Based on this above equation, what energy change occurs when 1.2 moles of methane react? All right. Actually, there's a lot of information there that we don't need. We just need to, actually, what we need out of the equation is to know how to treat the enthalpy. So enthalpy will be minus 434, right? Kilojoules per 1 mole of methane. Okay. 1.2 moles of methane are given. So all we have to do is multiply that times 434. Should give us our answer. $521 kilojoules. Or rounded off. Oh, it's in joules. Okay. So 521 times 10⁻³ joules. And let's see, we move it 2 places here, we just add those 2 here. 5.21 times 10⁵ joules. That would be A. Released. That's a negative. Okay.